Locked within the layers of our planet, like evidence at a crime scene, lie the silent witnesses to some of the most violent events in Earth's history. These are ancient ash deposits, the geological fingerprints of volcanic eruptions long past. To most of us, it's just dust and rock, but to a special kind of scientific detective, the forensic volcanologist, these layers are crime scenes frozen in time. This is the science of unearthing eruptions, of piecing together the story of a volcano's fury from the subtle clues it left behind. By sifting through this ancient dust, scientists can unravel the magnitude, intensity, and style of eruptions from thousands of years ago, giving us a vital instruction manual on how to prepare for the threats these giants pose today. The core of this work revolves around tephra. That's the catch-all term for everything a volcano spits out in an explosive eruption, from fine dust to giant blocks of rock. Every eruption produces tephra with a unique chemical and mineral signature, a fingerprint that can be traced across continents. This is the foundation of tephrochronology, a dating technique that uses these widespread ash layers as time markers. Imagine finding an ash layer in an ancient lakebed in Germany. A forensic volcanologist can match its chemical fingerprint to a specific eruption in Italy, and just like that, they've established a precise date for everything in that layer of the lakebed, from pollen grains to ancient human artifacts. This isn't just an academic puzzle. Understanding a volcano's past is the best way to predict its future. By reconstructing eruptive histories, we can create detailed hazard maps, identifying which areas are at risk from pyroclastic flows, lahars, and ashfall. The data from these ancient ashes, especially the amount of gas released, is also critical for climate models. It helps us understand how massive prehistoric eruptions affected global weather, which in turn helps us predict the consequences of future large-scale events. It's a science that bridges deep time with the pressing concerns of our modern world. When a volcano erupts, the ash deposit it leaves behind is the primary crime scene, and every feature is a clue. An eruption is rarely a single event. It's often a sequence of pulses with changing intensity. This is reflected in the layers. Take the famous eruption of Vesuvius in AD 79. It started with a sustained phase that deposited a thick layer of light-colored pumice, followed by a switch to gray pumice. This tells geologists that the volcano was tapping different parts of its magma chamber as the eruption progressed. Later, the style shifted to fast-moving pyroclastic flows, which left entirely different deposits. By logging these layers, we can reconstruct an hour-by-hour timeline of an event that happened nearly 2,000 years ago. The thickness of these layers is also crucial. An ash layer might be tens of meters thick near the volcano, but thin to just millimeters hundreds of kilometers away. By mapping these variations, scientists create what are called isopack maps, lines of equal thickness. From these maps, they can estimate the total volume of erupted material, which gives the eruption a score on the Volcanic Explosivity Index, or VEI. They can also figure out which way the wind was blowing at the time. But the real detective work begins under the microscope. What looks like uniform powder is actually a collection of different particles. There are vitric particles, which are tiny shards of volcanic glass. The magma itself, flash frozen as it was ejected. These are the most informative component. Then there are crystalline particles, minerals that had already formed in the magma before it erupted. And finally, lithic particles, which are bits of older rock torn from the walls of the volcanoes plumbing during the eruption. An increase in these lithic bits can signal that the eruption is becoming more violent. The shape of the glass shards is a direct window into how the magma shattered. Gassy, sticky magma, typical of explosive eruptions, shatters into angular, bubbly fragments. In contrast, runnier magmas can produce smoother, droplet-like particles. A key clue is the presence of blocky, pyramidal-shaped particles. This often indicates a phreatomagmatic eruption, one where magma has violently interacted with external water. like a glacier or a crater lake. The instant flashing of water to steam creates a unique style of fragmentation, leaving a distinct signature in the ash. But to definitively identify an ash layer, scientists need its chemical fingerprint. The workhorse for this is the Electron Probe Microanalyzer, or EPMA. It fires a beam of electrons at a single glass shard and measures the resulting X-rays, which reveals the precise amount of major elements like silicon, aluminum, and iron. For even more detail, they use a technique called laser ablation ICP mass spectrometry. A laser vaporizes a microscopic spot on the shard, and a mass spectrometer then separates and counts the atoms. This can measure trace elements in parts per million, adding incredible specificity to the chemical fingerprint. Perhaps the most exciting clues are found in melt inclusions. These are microscopic blobs of magma that were trapped inside growing crystals deep within the magma chamber, long before the eruption. They are tiny time capsules, perfectly preserving a sample of the pre-eruptive magma, including the dissolved gases like water, carbon dioxide, and sulfur. These gases are the engine of an explosive eruption. By analyzing them, scientists can measure the explosive potential of the magma and accurately model the climate impact of the released sulfur. Let's open our first case file, Mount Vesuvius, AD 79. We all know the story of Pompeii, but forensic volcanology gives us the minute-by-minute details. The eruption began around midday with a classic Plinian phase, sending a column of ash and gas 33 kilometers into the sky. For about 18 hours, this column rained down pumice, burying the surrounding landscape. In Pompeii, the weight of this ash, accumulating up to 3 meters thick, caused roofs to collapse. This phase was destructive, but survivable, giving many people a window to escape. But on the second day, the eruption changed catastrophically. The column collapsed, generating a series of pyroclastic flows, turbulent avalanches of superheated gas and ash that raced down the volcano's flanks. The deposits from these flows tell of a violent, high-energy event. This was the lethal phase. The intense heat, estimated at over 250 degrees Celsius even in Pompeii, caused instantaneous death. The fine ash carried in these surges enveloped the victims, creating the molds that archaeologists later filled with plaster to create the famous casts of their final moments. By mapping at least 6 distinct surge deposits, volcanologists have reconstructed the terrifying final hours of the city. Now for case file number 2, Tephra, around 1600 BC. This eruption on the island, now called Santorini, was one of the largest in human history, a cataclysm that obliterated a flourishing Bronze Age settlement and has been speculatively linked to the legend of Atlantis. It was a VEI 7 event, 100 times larger than Vesuvius, ejecting so much ash that it was dispersed across the entire eastern Mediterranean. This tephra layer is the key forensic evidence, found in sea cores, lake beds, and archaeological sites, from Crete to Turkey and even Egypt. Finding and dating this ash has been a monumental task. For decades, archaeologists and scientists debated the exact date. But recent analysis of tree rings, combined with radiocarbon dating of an olive branch buried by the ash, has now pinpointed the eruption to the 16th century BC. The ash itself tells the story. Its shape reveals that the eruption had significant phreatomagmatic phases, as seawater poured into the collapsing volcano. This would have generated powerful tsunamis, and indeed, on the Turkish coast, scientists found a chaotic layer of tsunami debris mixed with Theran ash. Tragically, within this layer, they found the skeleton of the first identified human victim of the eruption. The fallout was devastating. Ash layers on Crete would have smothered crops, leading to agricultural collapse. The vast amount of sulfur dioxide thrown into the stratosphere would have caused significant short-term climate cooling. Forensic volcanology has allowed us to piece together this regional catastrophe and its profound impact on the course of human history. Our final case file is more recent. Mount St. Helens, 1980. This eruption was different. It didn't start by going up, it started by going sideways. For months, magma had been pushing up beneath the volcano's north flank, creating a huge, unstable bulge. On May 18th, an earthquake triggered the entire north face to collapse in the largest landslide ever recorded. This instantly depressurized the magma beneath, acting like popping the cork on a champagne bottle. The result was a devastating lateral blast, a hurricane-force wave of hot gas and ash that screamed across the landscape, leveling 550 square kilometers of forest. Forensic analysis of the blast deposit reveals a chaotic, poorly sorted layer, but after the blast, the eruption transitioned into a more conventional vertical phase that lasted 9 hours, blanketing several states in ash. Scientists had to distinguish between the blast deposit and the airfall ash. They did this by looking at the layers. The blast deposit is always at the bottom, directly on top of the 1980 soil. The Mount St. Helens eruption was a stark reminder that volcanoes don't always erupt straight up, fundamentally changing how we assess hazards at similar volcanoes around the world. Of course, investigating a cold case that's thousands of years old is never easy. The geological evidence degrades. Volcanic glass can alter into clay, erasing its chemical signature. Erosion can wash away the original ash, making it difficult to calculate the eruption's true size. And in active regions, the geological record can be a confusing stack of different ash layers from different eruptions. Telling them apart requires high-precision chemistry to find the subtle differences that link a layer to its source. So why do we put so much effort into these ancient geological crime scenes? Because it has profound practical applications. By understanding a volcano's past behavior, its personality, we can create far more accurate hazard maps. Knowing where pyroclastic flows traveled in the past is the best guide for predicting where they'll go in the future. This is vital for land use planning, for developing evacuation routes, and for saving lives. This work also informs our climate models. Large eruptions can cause global cooling. The 1815 eruption of Tambora led to the year without a summer. To predict the impact of future eruptions, we need data from past ones. By analyzing melt inclusions from prehistoric supereruptions, like Toba in Indonesia 74,000 years ago, we can reconstruct their sulfur output. For a long time, Toba was blamed for a volcanic winter that nearly wiped out humanity. But recent models, fed with refined data from the ash deposits, show a more nuanced picture. While the cooling was severe, early human populations were likely sheltered from the worst effects. This work, a direct result of forensic volcanology, has refined our understanding of both climate dynamics and human resilience. The field continues to evolve. New tools allow us to analyze smaller samples with greater precision. AI is helping to speed up the classification of ash particles. As our world becomes more crowded, and as we grapple with a changing climate, the work of these geological detectives is more critical than ever. The silent layers of ancient ash still hold countless stories, and for the forensic volcanologist, the investigation has only just begun.